Microscopes have transformed society from the first discovery of cells and viruses to 21st century precision medicine and pharmaceuticals, helping to address major events such as the current COVID-19 pandemic. Microscopes that use intense lasers can now see biology with truly exquisite detail, 10,000 times smaller than the thickness of a human hair. This has revolutionized our understanding of cells and of molecules like DNA within them, and was awarded the 2014 Nobel Prize in Chemistry. However, the very best microscopes of today face a major problem. The very quality that makes them successful, their intensity, is also their Achilles heel. They use light billions of times brighter than sunlight on Earth. In such an intense field, biological samples can become sick or perish in seconds. Over the past decade, my team and I have been developing quantum microscopes to overcome this problem. In 2013, we showed that quantum microscopes can more gently probe biological samples. After 8 further years of development, this year, we showed that this allows the observation of biological structures that could otherwise not be seen. This was the main result of my PhD student, Katsuri Kasesio, and was a long-standing milestone of international quantum technologies roadmaps. Our microscope uses a property called quantum entanglement, which Albert Einstein described as spooky action at a distance. Entanglement is an unusual sort of correlation between photons that can be used to reduce the noise on light fields. Other microscopes need to increase the laser intensity to improve the clarity of images. By reducing noise, ours is able to improve the clarity without doing this. Our key challenge was to produce quantum entanglement that was bright enough for a laser microscope. We did this by concentrating the photons into laser pulses that were only a few billionths of a second long. This produced entanglement that was 1 trillion times brighter than had previously been used in imaging. When used in a microscope, our entangled laser light provided 35% better image clarity than was otherwise possible without destroying the sample. We used the microscope to image the vibrations of molecules within a cell. This allowed us to see detailed structures that would have been invisible using traditional approaches. Our work is significant because it shows for the first time that quantum entanglement can provide absolute advantages in sensing. We see it as an important first step into an exciting new era where quantum technologies allow us to explore living systems far beyond the limits of existing technology. This could have big ramifications, not only for microscopy, but also for many other areas, such as global positioning, radar, and navigation.